Right, hi y'all. Today we're going to be going over some basic op-amp, kind of like an op-amp intro, because we just started it, and I wanted to make sure y'all understood here, because this isn't as hard as you may think. So there are two basic rules we need to follow when dealing with ideal op-amps. The first one is that the inverting input and the non-inverting input have the same voltage. So the V minus must be equal to V plus. What else does that say about it? Well, that means that there is no voltage difference across the differential inputs. So if we were to go to this circuit here on the left, we can say this is plus minus. This is 0 volts. This is one rule that we must follow. Another rule is that there is no input current. Of course, this is all theory. This is all ideal. No input current. So what does that say? If we go to the left here, that means this current going into this op amp, the inverting input is 0. It's the same thing here. That must be 0. Now, this makes our op amp circuits actually much easier to solve because we don't have to worry about the inner workings of this op amp. And he did show pictures. It's just a bunch of BJTs with some resistors and then a single capacitor in the middle. And knowing these two rules gets you very far with op amp circuits. I mean, I'll show y'all a method that I use and almost everyone uses when dealing with these op amp circuits. It's called nodal analysis. If you want to look up other videos, you just look up this nodal analysis op amps, and it'll teach you how to do this. So the first thing that you do here is, well, I guess what we're trying to find is find V out and VS, right? V out in terms of VS. So find V out in terms of VS. And if we've seen homework 4, this is exactly what it asks you to do a lot of the time. So we want to find V out in terms of VS. Well, what does nodal analysis mean? What this means is we look at the nodes given in our circuit and we try and find the current through them using either you could use node voltage method essentially. So what we do is let's circle our nodes. We have this one, right? We'll call V out. And then we have this one here, and we'll call this one VA. All right, those are the only nodes in here, so let's create our node voltage equations for these. Let's start with VA. Okay, well, let's say we have the VA equations here. We'll start off with 0 is equal to. We'll start going through R1. So what's the voltage or the current through R1? We have VA minus 0 over R1. Plus, we'll go to the right. The current coming out of the node into the op amp is 0. Always. Then plus the voltage going through R2, which is VA minus, well, the voltage, the potential difference on the other side of R2 is V naught divided by R2. Okay. Now, let's do another equation for V out. So let's say V out. All right, so this one might be a little more difficult, mostly because we have some sort of current coming through here from the output of the op amp. That's weird. So that we wouldn't be able to make a node voltage method for, or create node voltage method equations for this. Well, this looks like we're kind of stuck. We have VA and V out, right? So remember, we have to deal with this rule here. V plus the voltage at the non-inverting input is equal to the voltage at the negative, or at the inverting input or negative input of our op amp. What does that mean? Well, that means with respect to ground, our Vs here is the voltage here. If that's true, that means Va is equal to Vs, because there's no potential difference across the inputs of our op amp. So what does that mean? Well, that means we can let Vs equal to Vo. Or sorry, not Vs, Va. I'm sorry. Va equal to Vs. Va is equal to Vs. Let's replace every Va with Vs. So now what we have is we have Vs minus 0 over R1. We can get rid of the plus 0, doesn't matter, plus Va or Vs minus Vo over R2, and that's equal to 0. And then here what we do is we solve for Vs in terms of Vo, exactly what we were saying we were going to do. Let's move this up here. So here we have, let me rewrite this maybe in a little better. We have Vs. Okay, that's the pencil, my bad. We have Vs over R1 plus Vs over R2 minus Vo over R2 equal to 0. We want to solve for V out in terms of Vs. We move Vo to the right side and multiply by R2. Okay, well, what we have then is Vo is equal to R2, and we'll take out Vs also. We'll say this is Vs times 1 over R1 plus 1 over R2. I hope y'all can see where I got that from. I skipped some steps with the algebra. But now what we can do is we can distribute this R2 here. And now what we get is Vo is equal to Vs. R2 divided by R2 is 1 plus R2 over R1. And that is our answer here. So going through this, what we've seen is we use nodal analysis, or just the node voltage method, and apply it to our op amp circuit. All right. Hopefully y'all got that. And just to let y'all know, when y'all get an answer here that is non-inverting, essentially we have a non-inverting op amp circuit. What this tells you is that, let's say we have some input. We have this small signal input, right? We'll say this is Vs. V out will actually be amplified in phase. When we get to an inverting amplifier, I'll show you what it would look like if it wasn't in phase, though. All right. So here, what do we have? Well, we have something a little different now. We have this op amp, a little more resistors, but of course we still have this negative feedback loop with R4. And it's connected directly to the output of our op amp, of course, to supply some current and create this sort of feedback, this negative feedback, which op amps all use to create an ideal circuit. Now, what do we do here first? Well, let's go back to the golden rules here. The two rules here are that there's no difference in the differential input, and there's no input current. So let's write that down first. So we have no input current. Well, that means I is equal to 0 here, and I is equal to 0 here. And then the other one was that the voltage at the inputs are the same. So what does that tell you? That tells you that, let me get a different color here. Let's get like green or some shit. Sorry. This voltage here is equal to this voltage here. So what if we just label this node as VA? And we'll label this node also as VA. And that gets us into the next step. We have to label our nodes. So we have that node, we have two VAs, and then we have this here, which we'll call as VO. Now, when you're doing your node and voltage method, if any node that you create is directly in line with the output of your op amp, you do not create equations for that. The reason, unless they give you a current coming out and they tell you to find it in terms of that current. The reason being is because the way op amps work is if your VS changes on one of the inputs, the output will try its best to create a current such that this input, this inverting input, will change to become the new VS value. So what I'm trying to say is the output will, or the op amp itself wants to keep this zero potential difference across its input, at so much so that the output that the current and voltage that it outputs really will change the inputs. That's why you have this negative feedback loop. So we can go here. All right, so now what we do is we've created our nodes. We can just do nodal analysis again. And you'll see after you do a couple of these, it doesn't get that much harder unless you start getting into more cascaded op amps. But all it really does is just get larger. It just gets more complicated, I guess. But this method stays the exact same. So let's make one for, let's say this is VA1 and VA2, and we'll say VA1 is equal to VA2, but I'm just going to make two different sets of equations. So let's start with VA1. So VA1, 0 is equal to, okay, well the voltage there, let's go to ground first. So the current through R3 is VA minus, or VA1 minus 0 over R3 plus. And then we have VA1. Let's go up through R4. VA1 minus Vout over R4. And then we have the input to the op amp. So that's going to be 0 always for ideal op amps. Now VA2. VA2 is a little different. Kind of looks like we have, what does that look like? They're not in parallel or in series. So how are we going to do this? Well, let's just create, again, nodal analysis, create node voltage equations. So VA2, start with VA2, and we'll go through the source. We'll go through the voltage source and that R1. So VA2 minus VS divided by R1 is the current through R1 plus VA2 over R2. All right, so let's see. Remember, VA1 is equal to VA2. So what we're going to be trying to solve in this is Vout in terms of, we'll say VA1. Sometimes they'll say V source, which would be our VA1, but I'll keep it as VA1 because that's what we have. So let's solve. Oh wait, never mind. In terms of VS, they give us VS, right? Yeah, hell yeah. Never mind. In terms of VS, they give us VS here. So, how do we do this? We have what? How many? 1, 2, 3, 4 unknowns. How are we going to solve this? Well, let's see. Okay, well, let's try and solve VA in terms of VS. Okay. So, VA1 is equal to VA2. Let's get these equations. So we'll say VA1, or VA2 turns into VA1. So we have VA1 minus VS over R1 plus VA2 over R2. Okay, can we solve for VA1 or VA2 in terms of VS? The reason being is because we want to solve for V out in terms of Vs. One way we can do that is we can solve for the Vs value in terms of one of our nodes. That might have been a little confusing, but what can we see here? Let's look at VA2. VA2, and if I were to draw this out, it might be a little easier to see. Let's say we have VA2, the potential VA2 at this point. We have this resistor and this voltage, and then we have ground. Vs, so plus minus is VA2, and we have R1. Well, this looks like a simple voltage divider. Of course, voltage dividers that we use usually have resistors, but this is the same thing. Vs will just be fixed. So the voltage across R1 will be fixed. So can we say that VA2 hold up. I fucked up already, damn it. Oh man. So what we're going to end up doing here is we need to solve for Vs in terms of our VA2. Okay, look, I'm going to show y'all here. Let's draw this little sub-circuit out here. So what do we have? Well, we have a voltage. We'll start with ground here up on top. Voltage with the negative side pointing, R1. And then we have R2 connected to ground also. So here, and then we have ground. Actually, it looks so dumb like that. We'll switch this up around. There we go. Okay. Actually, you know what? It would be better like this. Sorry. Let me redraw here. What I'm trying to show is it's a voltage divider. With Vs being the large voltage that it's applying. And we'll like draw a little plus sign up here because this is the op amp. But this is VA2. And VA2 has to be the voltage. Actually, this is not here. This is ground also. R2 and R1. VA2 is the voltage across R2. So, and of course, VA2 is also the voltage across R1 and Vs. So what we're going to do is we're going to create a voltage divider here such that VA2 is equal to Vs, and remember, VA2 is the voltage across R2, so we're doing R2 divided by R1 plus R2. So we've solved for VA2 in terms of Vs. And something we noticed, something here that we should notice is that, well, remember we're trying to solve for Vs or VO in terms of Vs. So what we're going to have here is a VO over Vs, or our gain. This is then, you can rewrite this as VA2 over Vs is equal to R2 over R1 plus R2. Now, remember, in amplifiers, we can come up here, how did we solve for Vs over VO? A lot of the times what we did was we multiplied something like this, Vx times Vx over VO, such that Vx is a dummy variable. Of course, these cancel, and you would get Vs over VO. This is going to be the same thing. We now have VA2 over Vs. What do we need? What do we need? So we have VA2 over Vs times what is equal to V out over Vs. What we need is V naught over VA2. This gets rid of the VA2 and leaves us with VOS, VO over Vs. So we need V naught or V out over VA2. How can we get that? Okay. Well, what if we use the equation from the nodal analysis that we've created? So let's go here, we can rewrite this, or even actually we can use this first one. This first one looks a little easier. We have VA and we have VO. In our case, this should give us the exact same answer. All right, so what we should get here is VA1 over R3 plus VA1 over R4 minus VO over R4 is equal to 0. Solving for VO in terms of VA1, you have add this to the right side, multiply by R4, so VO is equal to R4 times, we can actually take out a VA1, times 1 over R3 plus 1 over R4. Multiplying the R4 to everything here, we get VA1 times 1 plus R4 over R3. I got R4 over R3 and 1 by distributing this to both. This changes into 1 and this changes into this. So now let's divide by VA1, and let me start moving this stuff up here. We'll just put a little arrow. Now V out over VA1 is equal to 1 plus R4 over R3. And this looks exactly like a non-inverting amplifier there. So exactly what we have and exactly what we need. Let's plug it into this equation here. V out over Vs is equal to R2 over R1 plus R2 times 1 plus R4 over R3. And now we have V out, and if we want, we can put this there. That's usually how you would solve it. V out is equal to the input source times some resistance. All right, so that would be your answer here. If y'all had any questions about this part, I mean, you could easily do this VA2 in terms of VS, just doing this here. I see that in hindsight, this is probably much easier. You solve for VS over R1, multiply by R1, and you would end up getting something like VA2 1 plus R1 over R2. Oh, but that would be VS in terms of VA2, not VA2 in terms of VS. I guess you could just take the inverse. It would work out too. But as you can see, we didn't have to do this weird voltage divider. We could have just went straight from VA2 to this. So either way works. But you would get the exact same answer. I hope this one wasn't super confusing. I should have just went with the nodal analysis method. It would make so much more sense. But if y'all want to do that for yourselves here, it would be great for practice. All right, so let's move on to this one here now. What do we have? We have a, this one's a little odd. We have no feedback resistor here. Okay, that might be something to note. But first thing, 2 golden rules. This has to be 0 volts, and the input must be 0. Input current must be 0. So again, let's let this equal to VA and this equal to VA. They're both going to be VA. So what does that tell you? That means using this non-inverting, using that the feedback has no resistance, there's no voltage drop across that feedback loop. So this will also be VA. I hope y'all can see that. That node is going to be the same throughout. So let's create our equations. So use nodal analysis. We've already labeled our nodes VA and VO, which is essentially the same thing. So let's create an equation. We can say VA now is equal to VO, as we've done with this node configuration. So that means the inputs must be VO also. This makes it very easy. This is a one-step problem. So let's create our node voltage equations for VO. So we'll start with VO, and you can see here, this is the same configuration. This is another voltage divider, very easy. So what we have is VO over what? R2, the current going through R2, plus VO minus VS over R1 is equal to 0. Solving for VO, or I guess you could solve for VS in terms of VO or VO in terms of VS. But let's solve for VO in terms of VS. So let's do VO over R2 plus VO over R1 minus VS over R1 is equal to 0. Adding VS over R1, we get VS over R1 is equal to VO times 1 over R2 plus 1 over R1. Then we multiply by R1, we get VS is equal to R1 times VO 1 over R2 plus 1 over R1. Multiplying R1, we get VS is equal to VO 1 plus R1 over R2. So this is VS in terms of VO, but if you wanted to find VO in terms of VS, well, we just, let's see, what do? We can do VO in terms of VS. We divide by 1 plus R1 over R2. And we get VO is equal to VS divided by 1 plus R1 over R2. And that would be your answer. Of course, this is a voltage divider, so you would end up getting, it should be VO is equal to VS R2 divided by R1 plus R2. That could also be an answer. Given that this is in the same configuration as a voltage divider, and there's no feedback loop. There's no feedback resistor, I mean. So that would end up being your answer here. And now this last one, we have this sort of Wheatstone bridge with a voltage source in the middle. Okay, this one I wanted to leave for last because I wanted to show y'all that it isn't as bad as you may initially think, because whenever we're doing Wheatstone bridges, obviously you can't do like a regular solving method, and you can't simplify it because they're not in series nor in parallel. So how exactly are we going to solve this? Well, what are our steps? Let's first label the inputs of our op amp. We know this is 0. We know this is 0. We know the voltage across our inputs is 0. So that means the voltage in the inverting input is equal to the voltage at the non-inverting input. What do we know about that? Well, this is ground. This is 0 volts. If there's no voltage difference across the op amp, that means we have a virtual ground. What that means is this here is ground also. Very important to notice when you're creating this, and this is why the first step, of course, here is to apply our 2 golden rules. All right, so now we can label our nodes. Well, we have this node on the bottom right, we have this node up here, and we have 2 other nodes. We have this node and this node. Those 2 nodes might be a little difficult because, I mean, again, it's a Wheatstone bridge. You can't simplify anything. And you have, what, 3 different paths, branches for the current to go through? That doesn't look very nice. So here, we'll call this top one VB. We'll call this one V out. And, there's 2 ways you could solve for these nodes. You could call this one VA, and you could call, well, you go up here into this node, you have VA plus 6. You could also call the left one VA and the right one VA minus 6. But I don't want to have to deal with the negative, so let's keep this as positive. All right, we've labeled our nodes, and we've applied the 2 golden rules, and we've actually seen that there's a virtual ground at the bottom or at the base of our Wheatstone bridge. All right, so this one has numbers also, so we're actually going to be solving for a value in our most cases here. So let's solve. What do we want to solve for first? Okay, well, I mean, we can solve for VB if we want. That one looks maybe the easiest. So let's solve for VB. Let's do VB So 0 is equal to current going down. Let's do the current going down first. We have VB minus the voltage at the bottom, VO, over 30K, plus VB minus ground, we're going to the right now, divided by 10K, plus, okay, this is weird now. We have this weird thing, right? We have this branching. Now don't be fooled here. It's the exact same thing. We have our node voltages. So we have plus, what, VB minus, what do we want to do first? Let's do minus VA divided by 10K. And then I'll come down here, plus VB minus parentheses. Do not forget these parentheses. You will get, more than likely, you'll get them wrong. Minus VA plus 6 divided by 10K. All right, so that's our VB equation. And here we notice we have 3 variables, so we'll have at least 3 equations for the most part. So let's do VA next. We'll call this VA. VA, all right, well, the current going down, how can we do this? The current going down is VA, 0 is equal to VA minus, wow, the bottom is our virtual ground, so we have 0 divided by 10K plus, well, now we have VA minus, we're going up, VB over 30K. All right. Let's see. So we have VA minus VB over 30K, which is the current coming out. So we have these two. We have these two. Now this one is might be. Let's see. VA plus 6. I guess minus. That's VA plus 6. Yeah, VA. Oh, that would just be a supernode, right? Yeah, what am I talking about? I don't know, I'm getting tripped up over this. We would create a supernode here. Right, so now we actually have VA, and we have VA plus 6. Sorry, that was a brain fart. Holy moly. Plus, it's been a while, I guess, huh? VA plus 6 minus VB, we're going up from VA plus 6 through the 10K ohm. And then finally we have VA, or plus V. Right after I noticed. So right now I'm watching the video, I'm coming along with y'all. Right now I just finished the VA equation. So dumb I didn't remember that you could do supernode. It's been a while since I used the node voltage method. But right now I'm debating because we have 3 variables and we need 3 equations. So we have VB, we have a VA equation, but one thing I didn't notice was while I was doing this, I didn't notice there was one more node that I need to be taken care of because we have VO, right? I'm writing right now that I is equal to what, so we cannot write the equations for VO. We cannot write a KCL for VO because we don't know the current coming out of the op amp. But if you look at the bottoms of the Wheatstone bridge, we have a node right where I'm circling. I forgot, and I'm sorry, and now I'm labeling it as VC. From here, all we're going to do is create a very simple KCL equation for node VC. Now, we do notice that VC is the voltage, it's the virtual ground, essentially. Virtual ground means if one of the inputs for the op amp is connected to ground, that means the other negative or I guess the other input has to be ground, so they call it a virtual ground. And that's just because of one of the golden rules for op amps, for ideal op amps. And now, as you can see right now, I'm making the equations for the op amp, or no. Wait. Okay, this thing don't turn on, I guess, or stay on. My bad if my voice was bad or something. Or if it sounded far away. I was testing with it earlier. That's kind of what was happening. So, solving this equation, we have one unknown, one variable, or one variable, one equation. We have VA is equal to negative 1.5 volts. That's great, because you know what? We can plug this into here and find what VB. Solving for this, I'm trying to figure, not take too much time.